All right, so in the last video, we just kind of determined how we can introduce these allowable changes, delta F and delta C, into our objective function for profit so that we can kind of see how those numbers can change and still lead to the same decision. And what we saw is we just compared the slope of this line. We just solve it for y, put it into that kind of y equals mx plus b form where m is the slope. We just needed to guarantee that the slope of this line in this case was less than or equal to the slope of the top edge of our feasible region, which was negative 2/5. And in this case, again, in this case, that's the only inequality we really have. However, in other problems, you possibly could have two inequalities that need to be satisfied at the same time. So when we did that, we just said, well, as long as delta F and delta C satisfy this highlighted inequality here, then we know that the slope of the objective function line, that I'm calling L here, would be steeper than the top edge of our feasible region, and therefore our profit or our decision to maximize profit would be the same, even though our actual profit amount would change. So remember, our profit is computed by computing this quantity. So if our decision is the same, it's going to be x is 4 and y is 0. So if delta F is changing, that's going to change the profit. However, if delta C is changing, it's really not going to change the profit until we have to make a new decision, which would require us to actually make some construction grade lumber. Just doing the algebra, we got to a simplified relationship here that as long as delta F is a number greater than or equal to negative 80 plus 2/5 times delta C, any pair of changes for delta F and delta C which satisfy that inequality would lead to the same decision. Now we want to just kind of look at the individual allowable changes. This is very simple. We just pretend that only one of the numbers is allowed to change. So if only one number is allowed to change, what kind of range of values can the other value have and maintain the same solution? And it's very simple. You just look at this inequality and you plug in 0 for one of these numbers, delta F or delta C. So in this case, if we let delta C be 0, then delta F has to be bigger than or equal to negative 80. What that means is, as long as the profit for construction grade lumber doesn't change, the profit for construction grade lumber can decrease by $80 per 1,000 board feet before we have to make a new decision. So even if it decreases by $50 or $60 per 1,000 board feet, we're still going to make the same decision of processing only finished grade lumber. Our profit will go down, but it's still the best decision that we can make. And there's no upper limit in this case. If delta C is 0, the fact that delta F is greater than or equal to negative 80, of course, if the profit for 1,000 board feet of finished grade lumber goes up, then we're only going to make more profit, so we're not going to change our decision. And we saw that graphically. The line slope got steeper, it's not going to change our decision. But there is a lower limit. So when delta C is 0, we say is the allowable change for the finished grade lumber, delta F, has to be greater than or equal to negative 80. So we can actually have a decreased profit for the finished grade lumber. As long as that decrease is no more than $80, then we would make the same decision. Now on the other side, we can talk about the same thing. What if the finished grade lumber profit doesn't change? How much can the construction grade lumber profit change before we need to make a new decision? Well, we just plug in 0 for delta F. If delta F is 0, then we can solve this inequality for delta C. So delta C is going to have to be less than or equal to, let's see, 80 times 5/2. So 200. So we can see these in the notes. We go simplifying those two. So again, letting delta C be 0, using that inequality from the last slide, we see that as long as the construction grade profits don't change from 100, it stays at 100, the profits for the finished grade lumber can decrease by at most $80 per 1,000 board feet before we would have to make a new decision. And again, if we go the other way, if we let delta F be 0, then delta C can change up to an increase of $200. And again, this makes sense. If the profit for construction grade increases by a lot, then of course we would want to start producing that product because it's highly profitable. But what this is saying is it would have to increase by quite a bit, 200, from the initial profit, which was 100. So we would have to double, triple in size before we'd have to actually make a new decision. So in the context of this problem, is this model sensitive or not sensitive to changes in our profit per product or profit per unit for each product? Again, there is no exact way to answer this. It has to do with the context and it has to do with the numbers that we're looking at. So there's no formula for this. It's kind of common sense kind of thing. You just have to ask yourself, well, does that seem reasonable? Do you think that the profit, if a profit is $100 for construction grade lumber, does it seem like in a very short period of time, like a week or two, that the profit is going to change to triple in size? I guess that's feasible, but in the context of this problem, I would say probably not. So this number is quite large compared to the original number, which was 100. So it seems that small changes or reasonable changes in the market and how the profitability of construction grade lumber might change in the next few weeks or few months is not going to change probably that much. Therefore, we say the model is not sensitive to changes in the construction grade lumber. Similarly, if we go back to finished grade lumber, again, this $80 decrease relative to the $120 profit, which we now have for construction grade lumber, again, that $80 is on the same order of magnitude. It's more than half of the profit we already have. So it would have to decrease by more than half of its profitability before we would decide to change our lumber that we're going to produce, change our decision. So in this case, it's reasonable to say this model is not sensitive to changes in the profitability of the two types of lumber. Again, what that means, if the model is not sensitive, then it means that this decision should maintain its it should maintain the decision should be optimal for quite a bit of time. Again, can we quantify that amount of time? Not with the information that we have. We would have to have lots of other information, like maybe years and years of data based on how these numbers might change, and then we'd have to do some statistics to see what's the likelihood that the values will change or go outside of this range. And then at that point, we could then try to predict how long this decision would maintain profitability. So if we had that data and it said, well, most likely these numbers are going to change, but they're not going to change that much over the next 6 months or a year. So for the next 6 months or a year, we can basically plan on producing only finished grade lumber, focus on that, make that part of our business run as efficiently as possible so we can save even more money because we're not having to refigure out work schedules. We're not going to have to refigure out what kind of things to do. We're going to be making the same products all the time. So the consistency of that decision is good because you know it's going to be profitable, and it's going to stay that way for a long time. So you can save money by hiring your workforce to focus on only producing that kind of lumber. And you can allocate your resources, like your saw and your plane, in such a way that you use only what you need to use to make that decision happen, and then get profit from that portion of the company.